Hello everyone, welcome back to Next Dream 123. I am Akshay S, and in today's video we are going to discuss some of the most important and high-weightage questions from linear algebra. This video is especially useful for aspirants preparing for KSET, APSET, TSET and Maharashtra SET 2026. We will not just solve the questions, I will also explain the exam-oriented approach, important concepts, smart shortcuts that can help you save valuable time in the examination. So if you are preparing for SET exams or other competitive mathematics examinations, make sure you watch this video till the end. And before we move ahead, I have an important announcement for all the KSET aspirants. We are launching our KSET crash course designed with one goal in mind: complete syllabus coverage with an exam focused approach. The course covers major areas including linear algebra, real analysis, abstract algebra, complex analysis, ODE and PDE and topology. The course fee is just 1000 and it is available for a limited time. If you are seriously preparing for KSET and want structured preparation, important concepts, exam-oriented questions and focused revision, this crash course can help you prepare more systematically. The course is starting soon, so don't miss the opportunity. For course details and enrollment, contact us through the number provided in the description. Your success is our mission. Let's prepare together and crack KSET. Let's start with our first important question. Let V is equal to R3. Which of the following subsets is not a subspace of V? Okay, here vector space is given R3. We have to find the subset which is not a subspace of vector space V. See, first I will give a short tricks or shortcuts. Okay, then after that I will explain the concept of subspace. What is the meaning of subsets? Okay, subspace of V. Okay, vector subspace of. Okay, first, see, always remember these short tricks is very important. See, if you see in given sets, if homogeneous linear equation is given, okay, ax plus by plus cz equal to 0, if this is the equation is given, okay, this is always a subspace. The set always forms a subspace. Okay, like x plus y plus z. Here what is a, b, c? A, b, c are nothing but scalars, that means any real numbers. Okay, x plus y plus z equal to 0. Okay, or 2x plus y plus 3z equal to 0. Okay, like this, if these are this type of equations are given in the set, okay, given sets, then this is always a subspace. And the second one is if ax plus by plus cz is equal to d. Okay, if the set contains this type of expression, this type of equation, then is not a subspace. Not a subspace. Okay, always remember. And third one, if the set contain inequalities like x is greater than 0, xy is greater than 0, or xyz is greater than 0 or greater than equal to 0 or less than or equal to 0. If the set contain inequalities like this, then this is also not a subspace. Okay, always remember this is also not a subspace. And there is one more point. If coordinates, okay, are in the product that is equal to 0 or x, y, z equal to 0, if like this are there, okay, y, z equal to 0, then this is also not a subspace. Okay, see, by using these short tricks we can easily eliminate options. If you observe that this is a linear equation in the form of like this, okay, ax plus by plus cz equal to 0, like this, in the form like this. That means this forms, this is always true. Okay, this is a subspace. Actually this is a subspace. Okay, this is a subspace. this is a subspace, and x equal to y equal to z. See, if you write first, if you equate this two, we get x equal to y, that is nothing but x minus y equal to 0. This is also a linear equation in the form of like this only. Okay, if you take c is equal to 0, okay, this becomes like this. Okay, like this equation. Okay, similarly, if you equate this two, we get y minus z is equal to 0. If we equate this two, we get x minus z equal to 0. Okay, these are the linear equations in the form of like this. Okay, then this is also a subspace. This is also a subspace. And if you observe that the condition is given x, y, z equal to 0. Okay, this is not a subspace. This is not a subspace. And this is also linear equation which is equal to 0. Then this is also a subspace. This is also a subspace. Okay. Okay, finally, not subspace, we have to select option which is not a subspace. Then our option is C. C is the correct option for this question. Okay, for this question, C is the correct option. Okay, then what is the concept behind this? Why the C option is not subspace? Okay, why it is not subspace? See, let's consider some example. Okay, see, just I am taking a field is nothing but a scalar values or any real values, real numbers. Okay, this is the vector space V. Okay, this is the subspace. Okay, W. If you want to say W, if W is subset of V, okay, if W is a subspace of V, if you want to say, okay, W is a subspace of V, it should be satisfies three conditions. Okay, W should be contain. Okay, W must contain zero vector. Okay, zero vector. Okay, here we taking R3 means, okay, zero vector is 0, 0, 0. That means W should be contains 0, 0, 0. Okay. Second condition, see, in W, if I will take two vectors U, okay, another vector V, if I will add both vectors U plus V, this again should be belongs to W. Okay, and the third condition, if I will take alpha scalar value from field, okay, I will multiply with vector from W. Okay, this is also always should be belongs to W. Okay, if these three conditions are satisfied, then we say that W is a vector subspace of V. Okay, subspace of V or vector subspace of V. Okay, always you remember this. See, in this in the third set, just I will giving the name W. Okay, such that x, y, z equal to 0. This is the condition they given. Okay, let's consider this the W. We have to prove whether it is subspace or not a subspace. Just I am consider one vector U. Okay, see, 1, 0, 0, which is belongs to W. Yes or no? See, this will satisfy this. Okay, this is x, this is y, this is z. If I will multiply 1 into 0 into 0, I will get 0 only. Okay, this vector satisfies this condition. That means this is the member of this set only. Okay, this element is member of this set. Okay, similarly I will take one more example, V 0, 1, 1, which is also belongs to W. Okay, if I will apply this condition 0 into 1 into 1, this will satisfies. Okay, if I will take U plus V, that is equal to 1, 0, 0. Okay, if I will add coordinates at same place, 1 plus 0, we get 1. Okay, 0 plus 1, I will get 1. Okay, similarly it is also 1. Okay, see, if I will apply this condition, okay, 1 into 1 into 1 into 1, that is equal to 1, which is not equal to 0. Okay, that means we proved that this this element is not a element, not a member of W. Okay, this is not belongs to W. That means, okay, this set is not satisfied our condition U plus V, second condition U plus V belongs to W. Then W is not a subspace. That's it. Okay, you should remember this. Okay, let's discuss second question. Let U and W be subspaces of a finite dimensional vector spaces V with the dimension of U is equal to 4 and dimension of W is equal to 5. Then dimension of U plus W is equal to 7. What is dimension of U intersection W? See, we have a direct result. Okay, dimension of U intersection W, that is equal to dimension of U plus dimension of W minus dimension of U plus W. Okay, we're going to use this result. Okay, we're going to use this result here. Dimension of U intersection W, sorry, dimension of U intersection W, dimension of U is given 4, dimension of W is given 5, minus dimension of U plus W is given 7. Okay, if you simplify, you get 9 minus 7, that is equal to 2. Okay, our answer is option B. Option B is the correct option. Okay. Option B is the correct option for this. Okay, let's move on to third question. Let T is mapping from R7 to R4 be a linear transformation. Which of the following is not possible? Which of the following is not possible? Okay, which of the following is not possible? Okay, rank of T is equal to nullity of T. Okay, we know that one of the famous result, rank nullity theorem, or we call it Sylvester theorem also. Okay, we use this theorem. We know that rank of T, okay, nullity of T, that is equal to dimension of domain. Okay, understood? See, this is the domain, this is codomain. Okay, domain and codomain. Just see, this is the domain. R7 is the domain. R4 is the codomain here. Okay, let's what is the dimension of R power of 7 here? Dimension of R power of 7 is equal to 7. Okay, we know the dimension of R power of n, that is equal to n. Remember this result. Dimension of R power of n is equal to n. Okay, by using this theorem, we verify each option. Just take, see, rank of A is given. Rank of A in option A, we check rank of A is equal to 4. Okay, 4, nullity of T is equal to 3. 4 plus 3 equal to 7, which is equal to dimension of domain. Yes, it is true. Okay, it is possible. This option is possible. Okay, if you check option B, rank of T is 3, rank nullity of T is 4. 3 plus 4 is equal to 7. This is equal to dimension of domain again. This is also possible. This option is also possible. C option, rank of T is 4, nullity of T is equal to 2, 4 plus 2 is equal to 6, which is not equal to 7. Okay, this option is not possible. Okay, this is not possible. Okay, we check option D, T is not onto and nullity of T is equal to 5. Okay, you remember one important thing. If T is onto, if T is onto, if only if rank of T, that is equal to dimension of codomain. Okay, this is very important result. Okay, rank of T is equal to dimension of codomain. Rank of T is also nothing but dimension of range space. Okay, you should remember this also. Dimension of range space. Okay, that is equal to dimension of codomain. So you should remember this. Okay, here nullity of T is given by using the result. Okay, rank nullity theorem. We can find rank of T. Okay, because in the option it is given nullity of T is 5. Okay, and we know that dimension of domain is 2, sorry 7. Then rank of T is equal to 7 minus 5, 2. Okay, then what is a dimension of codomain? Dimension of codomain. Dimension of R power of 4. Okay, R power of 4 is the codomain here. Then dimension of R power of 4 is 4. Okay, if you observe that dimension of T which is not equal to dimension of codomain. Okay, this is codomain, dimension of codomain. Okay, then that implies what? T is not onto. T is not onto. Okay. This prove the C option is already given, T is not onto. Then this is also possible. Okay, we have to select which is not possible. Option C. Option C is not possible. That means we have to select. That is our option. Okay, we have to select that option C. Okay, C is the correct option here. Let's move on to fourth question. Okay, let's discuss fourth question. This fourth question is MSQ question, means multiple select answer question it is. Okay, MSC. Okay, multiple select answer. Okay, that means the one or more than options are correct. Okay, in this. Let it P is mapping from V to W be a linear transformation between finite dimensional vector spaces with the dimension of V is equal to dimension of W. Okay, that is equal to N. Which of the following statements is true? Okay, this is important. Which of the following statements are true? Okay, let's analyze. T is given mapping from V to W. Okay, it is the domain, it is the codomain. Okay, if dimension of domain equal to dimension of codomain, okay, that is equal to N is given. If dimension of W is equal to dimension of V is equal to, if dimension of W is given, that means dimension of domain and dimension of codomain is equal. If the both are equal, then T is bijective. Remember this is very important results. Okay, T is bijective and T is 1 to 1 and onto. Okay, and T is invertible also. Okay, T is bijective, T is invertible, and T is 1 to 1, 1 to 1 if and only if T is onto. Okay, these are the various results you should remember. Okay, you should remember this. This is very important result. Okay, T is bijective, T is 1 to 1, 1 1 and onto, and T is invertible and T is 1 1 if and only if T is onto. Okay, see if you verify the answers, T is always inverse, it is true, it is always true. If T is injective is nothing but 1 1. Okay, if and only if T is surjective, yes, surjective is nothing but onto, this is also true, is also always true. The C option is T surjective implies kernel of T is not equal to 0 set. Okay, the set contains 0 element. Okay, now see if you verify this, see always remember if T is onto, subjective nothing but onto, if T is onto, okay, if T is onto, okay, that implies kernel of T, okay, that is always equal to 0 set or the set which contains 0 element. Okay, and also just remember these results. T is onto, okay, if this kernel of T is equal to 0, that contains 0 element. Okay, then dimension of kernel of T, that is equal to 0. Okay. See, by this result also we can prove easily by Sylvester law also. See, this is a result, direct result. You can use it. Okay, from this result, this is false. This is a false statement. Okay, and by Sylvester law, okay, we know that rank of T plus nullity of T is equal to dimension of domain. Okay, dimension of domain. Okay, just by using this, if you observe that one of the important thing, okay, dimension of domain is n. They given rank of T plus nullity of T, that is equal to n. Okay, this is clear. And also we know that rank of T, that is equal to dimension of codomain. Dimension of codomain. Okay, rank of T is equal to dimension of codomain. Okay, here rank of T is equal to dimension of codomain is also same n. Okay, we know this. Okay, rank of T is equal to dimension of codomain. Okay, okay, when T is onto, if T is onto, rank of T is equal to, okay, if T is onto, rank of T is equal to dimension of codomain. Okay, we know, we already proved it is a onto. Okay, it is bijective means it is onto. Okay, by this, from this also, okay, if you take rank of T is n plus nullity of T, that is equal to n cancel, nullity of T is nothing but what, dimension of kernel of T. Okay, that is nothing but 0. See, from here also we can write, we got 0. Okay, that's why from this way also this is false. And come to fourth option, rank of T can exceed n. See, if T is on to, rank of T is equal to n. Okay, here the given rank of T can exceed n. That means the rank of T is greater than, what is the meaning of this? They given that rank of T which is greater than dimension of W. Okay, that is the given. But actually what? The both are equal. This is also false statement. This is also false statement. Okay, by this result, okay, by the direct result, we know that rank of T is equal to n. Okay, otherwise by ulta, we, if you know this also, if you say by using Sylvester law, rank of T we get n only. Okay, okay, this is the question. Okay, this is a concept based question. This is a very good question actually, very good question. Okay, this covers like bijective, one on to invertible, everything. This will covers all the results. That's why it's a very good question. And come to this question number 5, for which values of k does the system have infinitely many solutions? See, whenever it is given system of equations, we have various methods to calculate the system is infinitely many solution or unique solution or no solution. We have various methods. Rank method is there. Okay, and Roder reduced echelon form method. Okay, like matrix method. Okay, Kramer's rule method, and we have various methods. We have, see, I'm going to give here two methods. Okay, which method you feel easy, you can go with that method. Okay, one is rank method. What is rank method is, say first you write down argumented matrix. Okay, here A is a matrix, the coefficients of xyz matrix. B is RHS side, okay, constant column matrix, 1 2 3. Okay, RHS side elements, that forms a B matrix. Okay, okay, see, the first one is, if rank of A equal to rank of argumented matrix, okay, then okay, system has unique solution. System has unique solution. And second one is, if rank of A is equal to rank of argumented matrix, which is equal to R, but this is less than number of variables. Okay, number of variables, nothing but like x, y, z, like this. Okay, number of variables. Okay, then it has infinitely many solutions. It has infinitely many solutions. Okay, like next, the third one, if rank of A is not equal to rank of argumented matrix, okay, then it has no solution. Okay, this is the one method. Okay, you, if you want, you can follow this method. Okay, there is a one more method. That method is determinant or matrix method. Okay, this is a shortcut, actually shortcut method. This is a shortcut method. If the system like this, a1x, okay, a2y plus a3z, okay, that is equal to d1, okay, b1x plus b2y plus b3z equal to d2, c1x plus c2y plus c3z is equal to d3. Okay, first you should write a argumented matrix. Okay, the coefficients of x, y, z that forms a matrix, a1, a2, a3, b1, b2, b3, c1, c2, c3. Okay, then d1, d2, d3, this is a b matrix. Okay, first you find, okay, this is the a matrix, this is the b matrix. First you find the determinant of a. Okay, if determinant of a is not equal to 0, then system has unique solution. Okay, if determinant of a is equal to 0, there are two possibilities. Okay, one possibility is you just simply take the matrix, this matrix. Okay, a2, a3, d1, okay, b2, b3, d2, c2, c3, d3. Okay, just take copy paste this same. Okay, just I will reduce the size of this. Okay, just I will remove this part. Okay, see, if this is equal to 0, then it has infinitely many solution. Okay, if this is not equal to 0, then it is no solution. You remember this. Okay, this is a shortcut. Okay, otherwise if you very good in finding rank, then we go with this method, rank method also. They both are very good methods. Okay, you can follow any of this method. Okay, see, I am going to use this here. See, they clearly mention that is infinitely many solution. If it is infinitely many solution, definitely determinant of a is equal to 0. Okay, definitely determinant of a is equal to 0. That means just find the date 1, 1, 1, 1, 2, 3, the coefficients of x, y, z. Okay, 1, 3, k, which is equal to 0. If we x 1, 2k minus 3, 3 is a 9, minus 1, k minus 3. Okay, then if you expand plus 1, if you get 3 minus 2, which is equal to 0, then we get 2k minus 9 minus k. Okay, minus minus plus 3 plus 1, which is equal to 0. 2k minus k is nothing but k. Okay, minus 9 plus 4 is minus 5, which is equal to 0. That means k is equal to 5. 5k is equal to 5 is the correct option. That means C is the correct option. Okay, for this question, C is the correct option. Okay, if you want, you can just take the screenshot of this shortcut method. Okay, let's continue this question. Sixth one, let A is equal to, this is the matrix given, for which value of lambda is rank of A is equal to 1. Okay, see, for this also there is a short trick is there, direct short trick. You always remember, if determinant of, if it is the matrix is n by n matrix, okay, if it is n by n matrix, okay, if determinant of A is equal to rank of sorry if determinant of A is not equal to 0, if and only if rank of the matrix which is equal to order of the matrix. Okay. Second one, if determinant of A is equal to 0, which is equal to rank of A which is less than n. See, we have to just compare with vectors also. Okay. In matrices, each row we consider as a row vector, each column we consider as a column vector. Okay. In linear transformation, we have a concept like linear independent and linear dependent. Okay. If rank of A, if determinant of is not equal to 0, if rank of A is equal to n, and also which is considered as if and only if it is linearly independent. Okay, the vectors are linearly independent. Okay, vectors are linearly independent. And the one more thing, if it is rank of A which is less than n or determinant of A is equal to 0, we consider vectors are linearly dependent. Okay, linearly dependent. See, if you observe that, here rank of A is equal to 1. See, what is the rank of A is given 1, which is less than order of the matrix 3 by 3 matrix. Here n is equal to 3. Okay, that means it is proved that, okay, it is the given vectors are linearly dependent. Okay, what is the meaning of this? Okay, you see, you always remember there is a direct shortcut. Okay, for rank, if rank of A is equal to 1, okay, every row must be a scalar multiple of the first row. Okay, scalar multiple of first row. Okay, you should remember. And there is a one more point also, you should remember this. If rank of A is equal to 1, that implies all non-zero rows must be proportional. Okay, this is a very good result actually. Okay, you should remember this. Okay. Actually, the meaning of every row must be a scalar multiple of the first row. This is the meaning of linearly dependent. Okay, the definition of linearly dependent. Okay, linearly dependent. If determinant of A is equal to 0 or rank of A is less than n, okay, then vectors are linearly dependent. Or just you can remember this trick directly. If rank of A is equal to 1, all non-zero rows must be proportional. Okay. Okay, if you observe this, there are 3 columns, 1 comma 2 comma 3. This is a one vector. Okay, and second one is 2 comma 4 comma 6, and the third one is 1 comma lambda comma 3. See, if you observe that second one, if you take 2 common, we get 1 comma 2 comma 3 only. Okay, if you consider this is u, okay, this is 2u. Okay, that means these all vectors are proportional only. Okay, if you observe that this is also should be same. Okay, if you compare the both 1 comma 2 comma 3, that is equal to 1 comma lambda comma 3. If you compare, the lambda value equal to 2. Okay, lambda is equal to 2. Okay, this is also like 1 into some 1 comma lambda comma 3. Okay, if it is this is also u, if it is this is u, definitely lambda is what? 2 only. Okay, lambda is equal to 2. Then B option is the correct option for this question. Okay, and you should remember these results also. These results are also very important. Okay, if you apply the determinant of A is equal to 0, this we cannot get see, we will not get any lambda value if you apply this. Okay, that's why we should know the connections. Okay, connections of linearly dependent and linearly dependent vectors and determinant. Okay, determinant of the matrix is very important. Okay, and this is a question number 7. What is given? Question number 7. If A is a 4 by 4 matrix with the determinant of A is equal to 5, what is the determinant of 2 A inverse A power of t? See, we have to use the properties of determinants. So the first one is determinant of A is always equal to determinant of A transpose. This is the first property. The second one is determinant of k times of A. K is any real number. Okay, k is any scalar value. If you take k outside, we get k power of n, determinant of A. And the third property, determinant of A into B. This is used as determinant of A into determinant of B. Okay. And one more property, determinant of A inverse. This is also same as 1 by determinant of A. This is also very important property. Okay, very good property actually. Okay, we're going to use all these properties here, and always remember determinant of A plus B is not same as determinant of A plus determinant of B. Okay, this is also very important. Okay, like this we have various determinant properties also. Okay, first we discuss this question, later I will list remaining determinant properties also. See here, there is, if you take 2 is a scalar value, means real number, you take 2 is common outside, we get 2 power of, what is the order? N is equal to 4 here. Okay, 2 power of 4. Okay, into determinant by the determinant of A inverse into A transpose. Okay, 2 power of 4. 2 power of 4 is nothing but 2 into 2 into 2 into 2. That means multiply 2 into 4 times, we get 16. This 16 into, apply the third property, we get determinant of A inverse into determinant of A transpose. Then 16 into determinant of A inverse is nothing but 1 by determinant of A, and determinant of A transpose is also same as determinant of A. They both are get cancels. Okay, we get 16 is the answer. Okay, our answer is 6, option A. Option A is the correct option for this question. Okay, you should remember all these properties is very important. Okay, and this is the 8th question. This question is related to eigenvalues. Okay, here A is a 3 by 3 matrix. Okay, for the matrix A, the eigenvalues are 2, -1, 3. Okay, then what is the determinant of A square minus I? Okay, first find the eigenvalues of A square. These eigenvalues of A. The eigenvalues of A square is, just take the power 2, 2 square minus 1 square, 3 square. Okay, here power is 2. Okay, for each eigenvalue you take the power 2. Okay, then we get it is 4, it is 1, 3 square is 9. Okay, these are the eigenvalues of A square. Now it is identity matrix. What is eigenvalues of identity matrix? 1 1 only, 1 1 1. Okay, identity matrix. Okay, eigenvalues of identity matrix is 1 1 1. Okay, then just see A square minus I is given. A square minus I, just simply take eigenvalues of A square minus I. Okay, that means subtract the both. 4 minus 1 is 3, 1 minus 1 is 0, 9 minus 1 is 8. Okay, we know that one of the very important property, determinant. Okay, determinant of the matrix. Okay, det equal to product of eigenvalues. Okay, we want a determinant of a square minus I, that is simply equal to product of eigenvalues a square minus I. Okay, that means determinant of a square minus I equal to product of all the values 3 into 0 into 8, that is equal to 0. That means option A is the correct option. Okay, this is a very important property. We have a one more property also. Trace of the matrix is equal to sum of eigenvalues. This is also one of the important property you should remember. Okay, important results in eigenvalues. Okay, let's discuss ninth question. A 3 by 3 real matrix, okay, has a trace 6, that means trace of the matrix A is given 6. Okay, 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 trace of the matrix A is given 6, and all of its eigenvalues are positive integers. Okay, what are the eigenvalues? Okay, let's see. We know that sum of eigenvalues is equal to trace of the matrix A. Okay, let's check options wise, all the options here one by one. Okay, um and det also given 6, so this is also very important. Det of the matrix A is equal to 6. First we check the first option. Okay, just take the sum of eigenvalues 1 plus 2 plus 3, that is equal to 6. Okay, what is the determinant? Determinant of A is nothing but product of eigenvalues 1 into 2 into 3, 3 2 is 6. Yes, this is satisfied. Okay, this is our option actually. Okay, A is the correct option. And we check B option also. If you take sum 2 plus 2 plus 2, which is 6, but 2 into 2 into 2, which is not equal to 6, that's why we eliminate B option. And C option, if you take the product, this is also not equal to 6. If you take the product, we get 0, which is not equal to 6. We eliminate D option also. Okay, only A option is the correct option.